All right. Hello, everyone. Welcome to our March Observatory Open House. My name is Lawrence. I'm one of the observatory coordinators here for our people on Zoom. Akanksha, our other observatory coordinator, is there with all of you. Before we get started, I'd like to acknowledge that we're gathered here tonight on the traditional lands of the Anishinaabe and Haudenosaunee peoples on a beautiful, clear night like tonight when so many of you are here with us to talk about astronomy. Really thankful to be gathered here tonight with you. Tonight we have a really great presentation from Nick Arora. But before Nick has asked me to introduce that within the coming months, there's going to be an Astronomy on Tap happening at Mansion. Our speakers will be Ken Clark, Ryan Carr, and our very own Sarah Satterboy. So mark that in your calendars from now. I'm sure you'll be hearing a lot more about it in the coming weeks. But Nick was very adamant that he's memorizing your faces and he expects to see you there since you've been told from now. So we have a really great talk tonight from our very own Nick Arora. Nick is a postdoc fellow here at Queen's University and the McDonald Institute outreach coordinator. Nick's originally from India, but he did his PhD here at Queen's University studying how galaxies form and evolve over the 13.8 billion year history of the universe. Aside from that, Nick was also the observatory coordinator for many years during his PhD and his master's, presumably standing right where I'm standing, doing a better job than I'm doing right now. With him as well, we have Connor Stone, special guest in the audience tonight, who is also an observatory coordinator. Currently, Nick focuses on comparing simulations of galaxies to real data to make those simulations better and creating educational spaces that enable experts to share their knowledge on broad, diverse audiences. Tonight, he'll be telling us all about looking for aliens, specifically because Netflix doesn't have good enough space dramas. So for ado, I'll pass you on to Nick Arora, and I'll see you all up in the dome. Oh, okay. I'm assuming everyone can hear me. I only come to this talk for the class. You all clap for me, so I think that's the end of the talk. Let's go out and see this space. No? Okay. All right, looking for aliens because Netflix just is very boring. That's what I'm going to be shedding some light on today. But before I get started, it is International Women's Day. And I wanted you guys to clap in a minute, but sure, we'll do this again. So I have the pleasure and the honor of working in this space right over here with many, many dedicated and talented scientists. Sarah Satterboy, who's the director of the observatory, Akanksha, who's the coordinator of the observatory, and many, many volunteers that you're going to see today interact with and have a minute to sort of just get infected by their passion. And so I just wanted to take this minute to acknowledge that passion, acknowledge that honor that I have, and take this minute to really not congratulate, but celebrate this together. So how about we now do the round of applause? All right, back to aliens. I truly am bored of Netflix, and that's truly why I wrote it. Okay, it's also kind of topical. There was a time, this is a blank screen, don't worry. This is intentional. Last November, something happened in the sky that made a lot of news, right? This is News Nation, not really the best source for your news. Don't go there. But let's start here. Drone sightings over Long Island Airport sparked concerns. Associated CNN picked it up. Mysterious sightings drone. Associated Press Tech picked it up. Back when they had access to the White House. This went worldwide. Canada picked it up. We saw it here. Like some people in Trenton and around Toronto also noticed these sightings. Governments in the UK and Australia picked that up as well. So it wasn't a recently big thing, big enough that a Wikipedia page needed to come up for this. You can all go visit and learn about all of the drone sightings that happened and all of the maybe extraterrestrial connections that are being made that may or may not be true. There was a time, maybe it was a small news day, but I had to go out in global news and talk about this. It was the most uncomfortable interview I have done in my life. The interviewer apologized to me and then ended the interview by saying, well, this wasn't the extraterrestrial news I was hoping for from you today. And so this really took me back. As a science communicator, this is a very, very common question I get. Are there aliens?
Yes, there are. And no, we're not going to go talk about Area 51, but by the end of today, I'm going to try and give you some maybe math or numbers, just pure numbers, reasoning of why I think there are aliens. And also sort of get you on a relaxed level so that you don't think I'm a cookhead or a whack job and thinking about tinfoil interaction. Let me put it that way. So let's talk about our modus operandi. I did use ChatGPT and Apple's artificial intelligence very much in this talk, and that's going to come out a couple of times. So I asked Apple's artificial intelligence to make an alien for me. This is what it came up with. I'm very, very sorry to disappoint you. This is not what I'm going to be talking about. What I'm going to be focusing on is the numerous efforts in the really brand new field of astrobiology that is going on to look for evidence of life in the universe. And I want to sort of put forward a foundation to this talk right now. It'd be really cool if we find extraterrestrial life. It'd be super cool. But as a scientist, that's not what I'm worried about. What interests me a lot more looking at these missions is what is the physics, what is the chemistry to form life in different scenarios. And I'm going to try and focus on that today, if that's okay with you guys. Okay, so we're going to try focus on the science of extraterrestrial life. If I could start every talk, I would start it here. And the main message that you should take from here is that space is vast. This is a picture taken by the Hubble Space Telescope. This is called the ultra-deep field. Just as a reference, this is a patch of sky that is roughly equal to you holding a grain of rice at an arm's length. Okay? Put another way, if you wanted to get a soda straw, Canadians call them pop straw, and look through that, if it was 2.5 meters wide or long, this is what you would see. And there's something super interesting you're seeing. Every little point of light that you see in this picture is a galaxy. Every single one of them. So space is actually littered with galaxies. Now let me disappoint you very quickly. There's not a single galaxy in this image that we will ever be able to. Why? Because space is vast. So let's come back to our own galaxy. This is the Milky Way. For those of you who attended the talk here last month, not week, this was presented to you. This is done by the Gaia space mission. And what this is showing you is the most up-to-date picture of the Milky Way, where each point, each pixel, each dot that you see is a star. This thing contains about 1.2 billion stars. And yes, for the next little while, we're going to be dealing in billions. So brace yourself. Astronomy is all about big numbers, big numbers. 1.2 billion stars in this. Just as a reference, the previous catalog of stars that we had in the Milky Way was roughly 40,000. So this is a huge, huge advancement. And Gaia is still releasing data. This number is going to continue to go up. So now let's talk about some big, big, big numbers. There's roughly, I'm sad because I don't have this is going to happen regularly, isn't it? I'm cursed, guys. Or maybe the aliens are around. I know. This is going to suck. Sorry, I didn't say that. It's going to be exciting. We're going to figure this out. Maybe this is an issue with my own computer, but anything. There's about 400 billion stars in the Milky Way. Just a back of the envelope number that I'm throwing out there. And about 20 billion of them are sunlight. The reason why I try to make that distinction right over here is because not every star can host a planet. It turns out the bigger the star, the sooner it will die. And the bigger the star, the more energy it releases. And as a result of that, the dust around the star that can actually eventually lead to a new brand new planet will be destroyed pretty quickly. So you do need sunlight stars or somewhere around that to actually form planets, okay? But you can't just put a random planet anywhere. It turns out there needs to be a specific place, a specific distance from the star itself, where you can put a planet that could host life, okay? If you're too close to the planet, it's too hot. Think of Mercury, think of Venus. If you're too far away, it's too cold. I do love the cold, Mark sitting here, he's never actually seen me complain saying that it's actually too cold. I love it. When I was 8 years old, I asked my dad on my birthday to give me a screwdriver so that I could build a rocket space and go live in Pluto because India was too hot. Anyway, but we're gonna do some really creative things with the too cold part over here when it turns to looking for life. But really, there's just this simple middle zone that is called the habitable zone or the Goldilocks zone, where you can find life. So if we just do some random, not a random, but if we just do a simple extrapolation of how many planets each of these stars can have, each of these 20 billion stars can have, and how many of those planets could just be in the right place, the habitable zone, we come to about 4. Am I counting by numbers? Yeah, 4 billion. Okay. So there could be 4 billion planets that are roaming around sun-like stars. I'm just trying to convince you about life in the universe by still being super conservative. These numbers are probably off by factor 5 at the best, which means there could very easily be 20 billion planets in our own galaxy around a sun-like star. Let's say only 0.1% of those planets actually host life. So just right now on March 8th, 7:16 p.m., there's about 4 billion planets that could support life. The Milky Way is roughly 10 billion years old. Let's again be conservative. In that 10 billion years, the first 3 billion years were too explosive, too violent, too cataclysmic, could not form a planet. That still roughly gives it about 7 billion years where you could continuously form planets that could support life. Just right now, there will be about 4 million. Okay, so let's keep this number in mind. I'm going to come back to it. We're about a quarter of the way through the third stage, roughly. I lied. Okay, so what is life really? What truly is life? So now we have a number of planets that could support life. When I, as a scientist, or my colleagues as a scientist, actually go out there to look for life, what are they looking for? Ask ChatGPT. And this is what ChatGPT said. Well, it's that awkward moment between birth and death where you desperately try to figure out what you're doing while pretending you have it all together. It's being handed a game with no rule book and still trying to win it. I think some days I truly do feel like this, but not today. Biologically or on a scientific scale, there is a definition. Yeah. Oh, sorry. I guess I have to stand right here. Biologically, there is a definition of life, and I think that's better than what ChatGPT came up with. ChatGPT is funnier though. So there's 5 main criteria that one needs to figure out life. The first thing is metabolism, which means you take in some kind of fuel, convert it into energy, and grow yourself. A lot of us are doing that right now. I have unfortunately finished growing. I'm on the downward hill of my life. As some of my friends who are currently in the crowd like to tell me very often. You reproduce that organism quite often. You have a defined cell structure. Both plants and animals have dedicated cells. In your grade 7 biology, you might have learned about the difference between plant cells and animal cells. So there's defined structures of those cells. And finally, you respond to stimuli, which means if someone pokes me, it hurts because I bruise like a peach, apparently. Okay, so when it comes to life, this is life, but so is this, okay? And when it comes to astrobiologists actually going out there and looking for life, it's really the latter thing that people are looking for. It's really those microorganisms that we're looking for, or signatures for that. We're going to talk about signatures in a minute as well. But I would like to quantify this even more because I am crazy and I like numbers more than words. Turns out a few scientists in this world agree with that opinion of mine. So someone came up with the Kardashev scale. Okay? The Kardashev scale is basically categorizing civilization or organisms into particular categories depending on what kind of energy sources that they use. Turns out you can make it a continuous thing. I've made it like there could be only type 1, type 2, or type 3, but humans are roughly 0.73. So what are type 1, type 2, type 3 civilizations? Well, type 1 is a civilization that actually utilizes all of the energy resources from the planet. Okay. Our planet keeps us warm for a little while. That means there's some energy happening over here. And we do use it. Think of coal, think of the sun. Actually, no, the sun doesn't count right now. Think of coal, think of rivers, think of wind, think of nuclear decay. Just as of last 2 weeks, I've figured out this is gonna, I have a very nice flow, and this is gonna hurt my flow quite a bit. But we could make this really productive. This could also be a chance for you guys to interrupt me and ask questions if you have. Yeah, so just utilizing all of the energy resources from the planet. Type 2 moves a step further and utilizes, along with the planet, all of the energy from its associated star. So in our case, that would be the sun. How do you do that, one might ask? Well, we're kind of doing that with solar panels and whatnot, but that's too preliminary. Who's heard of a Dyson sphere? Oh, a few of you. Good, good, good. So what you end up doing is you basically end up placing a lot of mirrors around the star, cover the star completely so that you can get all of the energy. Those mirrors then have cables on them, and then you relay the cable back onto the Earth to actually use that energy. Now I am aware that this particular plan that I've suggested has clear logistical issues, but don't worry about it, guys. Please. We're going fast here. Okay, but astrophysically, there are scientists out there trying to look for Dyson spheres or stars with Dyson spheres around them. And the idea here is that if you have a sun-like star, a star like our sun, and you put a lot of mirrors around them, the mirrors will actually heat up and give up a lot of infrared radiation. So if you start to find stars in infrared, that could be signatures, weak signatures for Dyson spheres, okay? We can see stars in infrared as well. We can see our stars in infrared. We can just see our sun in infrared as well. Ooh, by the way, side note, ask me about that later. There's a really cool story behind how we figured out infrared radiation using the sun. And it blew my mind when I learned about it. And I would like to do the same with you guys. There's a type 3 civilization as well that, along with our own star, gets to utilize all of the energy from the galaxy. Remember, there's about 100 billion stars in our, actually more than 100, 400 billion stars in our galaxy. Getting to use all of those, getting to use the black hole sitting at the center of our galaxy. Ask me how one would actually do that. Actually, ask me now. The answer is to actually start using radio radiation coming to us from the hot material that's actually guzzling into the black hole to start using some of the energy. Okay, let's do a quick midway recap because I seem to be going on time, which is amazing. Okay, 400 billion stars in the universe, in our galaxy, about 20 billion of them. Yeah, our sun-like, there's each of them, just on a rough conservative estimate, close to about 4 billion stars. And then there could be about 4 million of them, yeah, that could support life. Here's another question that I want you guys to ask. How long does it take for you to move up through the Kardashev scale? If humanity started roughly, let's say, 1 million years ago, how long will it take us to go all the way to type 3 civilization, right? Let's take 1 million. 1 million for the evolution of the universe, the evolution of a galaxy is like this. It seems like a long time to us, but it's actually very quick for the evolution of the universe. So humans stand over here. Oh, as another side note, this line that I have drawn over here is an accurate representation of humans on the Kardashev scale. I actually measured the length of this bar and then put that line about 0.73 of the way there, okay? So people that are much smarter than I am believe that it would take us another 200 to 400 years to actually make it to a completely type 1 civilization. And it would take us about 3,000 years to travel our way through a type 2 civilization. The idea over here is that you are actually covering through the vastness of space very, very quickly. But at the same time, you have technology that exponentially is growing very quickly. And then takes another 100,000 years to actually become a complete type 3 civilization. So for the evolution of humanity, which is roughly 1 million years, 100,000 years, not that much. It's only 10%. Not that bad. The Milky Way is roughly 10 billion years old. It takes about 200,000 years. Actually, you know what? I said wrong. It takes about 500,000 years. I don't really care about this number that much because it's still going to blow your mind the rest of the slide. It takes about that much years to actually make your way to be a type 3 civilization, which means that any given time. So, as I said, on March 8th, at 7:25 p.m., there's about 30,000 type 3 civilizations that should exist. Where is everyone? If there are that many planets that can support life, if it's that easy to make life, and if it's that easy to start utilizing energy resources, heck, we figured it out, where is everyone? And so that brings me to the Fermi paradox. This is what I kind of demonstrated to you. This is a paradox of just the sheer vastness of space, the sheer counting that you can do in space, and yet not being able to find life. There are solutions to solve this paradox. There are ways to reason out of this paradox. I don't have time. But yes, once again, if my computer goes off for right now, no, it doesn't. Ask me about this later. We're going to move to part 2 of our talk. So, elements for looking for life. Now I want to talk to you guys about when we go out there, look at planets in our solar system, outside our solar system, what exactly are we looking for to look for signatures of life? And I've put about 5 elements in the periodic table that are very, very important for life. Each of them have a specific place or a specific role that they play in actually promoting life on a planet. So when we go out there, when we actually have missions go up there, they're actually looking for combinations or some kind of elements for this for life. Within our solar system, there's roughly two more planets along with the Earth. We think Earth has life. Thank you, Mark. That's what I wanted, guys. Show some life. I'm really good at fun. We think there's at least 2 more planets that kind of sit within the habitable zone. So that's Venus and Mars. So when it came to looking for biomarkers or biosignatures on outside of our Earth, those are the first culprits. Okay, let's go through Venus. Venus is a quite interesting planet. It's quite hot. I don't like being there, but if I could be there. In 1982, Russia's Venera 13 went there and was corroded and died in roughly 2 hours or something. But it was able to send us this picture. And you can see it's quite barren. But we still think Venus could host life, and it would host life in its clouds. That's kind of the idea. Venus has a thick 20-kilometer layer of clouds. And it's possible, the temperature, of course, varies in that cloud. And so there are places where Venus could actually host life within that cloud coverage. Come 2023, there was a particular element, molecule that was discovered in the atmosphere of Venus. It's called phosphine. It's a combination of phosphorus and H3, or 3 hydrogen atoms. H3, look at me. Anyway, 3 hydrogen atoms. And using radio telescopes, scientists were able to find signatures of phosphine. Now, this was a very big discovery back in the day. Where's Lawrence? Oh, Lawrence. Back in the day, when we were running the observatory, the pandemic hit around that time, and we still wanted to talk to you guys, so we started a podcast series, and that was our first episode, phosphine on Venus. It was very exciting. Then it was proved wrong. It was sad because we really wanted that exciting discovery to stay. I'm going to stop here. I'm going to take some. I'm actually going to take some time on the slide a little bit longer and go in a complete tangent. And that tangent is kind of important for me as a science communicator. I think it was quite profound that the discovery of phosphine actually was proven wrongly. It shed light onto something really, really important about the scientific method, and that is reproducibility. I think it's super fundamental to emphasize that the results or the things that we know about our universe, about our nature today, are the things that we know as of today. It's, well, not totally, but it's possible that tomorrow some new results come out and flip our understanding upside down. In fact, that happens quite regularly. And so one of the key things when it comes to building scientific experiments is to actually reproduce previous results. I have undergraduate students who work with me do that quite regularly. In fact, if I drop this is quite expensive. I'm not going to do that. Yeah, right here. If I drop this today and it does not go down, I think Newton is in trouble. But that's a good thing because we understand something new about gravity. The whole point of being a scientist is to break our current understanding. That's where the new things lie. And that's what I wanted to take that digression just to talk about. So discovery of phosphine on Venus completely being proved wrong was actually a good thing in some ways. It actually highlighted how important the scientific method is. Now that I'm done with my digression, I can reshare my screen. I don't know why this keeps happening. I do have my boss or my partial boss sitting in the audience. I'm not going to name who it is, but maybe he can think about buying me a new laptop. Oh. That was great, Mark. Thank you. Okay, moving on. I want to go to Mars. That was kind of the next big thing that happened. We landed also in 2021, a rover on Mars. He actually just left the call. I guess he's bored. In 2021, a rover on Mars landed. It was called Perseverance. It is very lovingly known as Percy. This is Percy sitting on Mars. This is Percy in Lego form. And for a mere cost of $129.19, sitting in your bedroom. I'm not going to confirm or deny whether this sits in my bedroom right now or not, but you can do that. On Perseverance, there are two particular experiments. The first one called Sherlock that lives in its arm right over here. And the idea of Sherlock is to look for biosignatures on the terrain or the soil of Mars. This is Sherlock seen in zoom in. The next one that is quite important, I find really cool, is Moxie. This is a QR code. If you want to pull out your phone and scan your QR code, that would be pretty cool. Do not play the sound. It is an audio. What Moxie does is actually tries to make oxygen out of carbon dioxide on Mars. One of the key things, sorry? Yes, like trees, exactly like trees. One of the key missions of Perseverance is actually try and understand how we can actually go and put humans on Mars. And as far as last I checked, humans actually use oxygen. And this thing is trying to figure out how to make oxygen out of carbon dioxide. Okay, that was our own solar system. What about other solar systems? In comes December 25, 2021. This particular thing behind me was launched. This is called the James Webb Space Telescope. And one of the pillars of science of James Webb Space Telescope was actually to look for life on other planets, or study exoplanets or other solar system planets. This was the first picture that was released out of James Webb Space Telescope. It happened in July of 2022. And guys, I'm not lying to you, that was my chair when I saw it. Has nothing to do with planets, but just thought I shared that. We're friends, right? That was a cool picture. That was a really cool picture. There's someone in the crowd, once again, I'm not going to name who jinxed this as of yesterday. Well, there we go. Now know who that is. Here's James Webb looking at 4 giant planets in our solar system. It makes really, really cool pictures, but it can also look for planets on other solar systems. Well, how do you do that? It's actually quite complicated and simple at the same time. You basically you stare at a star and hope that a planet that's going around the star actually come in front. I actually started this sentence at the wrong time. Okay, actually come in front of the star and dim it just a little bit. Just as a reference, you're looking at a dim of about 6%, and things that are already dim, like stars in the night sky, this is a very, very hard thing. But that's how we look at planets. We think if a star's brightness dims, it's probably because the planet has to be. Right, so you try to do that. But here's the crazy thing. If this planet has an atmosphere, the light of the atmosphere, the light from the star going through the atmosphere will actually change. Will actually change. And James Webb can detect the reason why that light changed. I know, this is super crazy. We can barely study our own atmosphere, and we're looking at gas on other planets as well. This is super crazy. Here's the first result that James Webb released about that. On the x-axis, or on the horizontal axis, you have color, or basically wavelength of light, and on the y-axis, you have how much light was blocked by the star. These peaks and troughs that you see are signatures of different kinds of molecules in the planet's atom. The key thing that you see is water. This water is not ocean or Lake Ontario. This is vapor, really, in the atmosphere that James Webb is picking up, which was a really good sign. The cool thing, this thing had been done before, but only for nearby things. So the data that we had like this for a planet was roughly about 10 light years away. Welcome back, Mark. We completely moved on. This thing, James Webb actually did it for 1,100 light years away. For a planet, 1,100 light years away. That's 100 times further than the data that we have, right? Here's another cool one. This is about 700 light years away from us. And now, along with water, you can start to see other molecules as well. Carbon dioxide, sulfur. Remember the 5 elements that I showed up very, very quickly and breezed past them? Well, sulfur was one of them. Sulfur dioxide is right there, right? So these are some really strong hints that this planet might host life. It's a hint, but these are things that we're trying to look for in trying to understand planets. The last 3 minutes I have, the last 5 minutes I have, the last 10 minutes I have, we're gonna look towards the future, okay? So next on looking for aliens, I kind of now want to move away from the title of the talk being looking for aliens and go to looking for life. I think that's a more profound title. Last year, 2024, this thing went up. It's a box for you guys, but this thing is called Europa Clipper. It's gonna take 10 years or 8 years now, 2024. Yeah, about 7 to 8 years to reach this particular ball of ice. Anyone know what that is? Europa, oh wait, it's in the name. Yeah. I'm nervous, guys, I'm nervous. This is Europa, which is a moon of Jupiter. It's really exciting to us because we think most of it is ice, but underneath this ice, we think there's liquid water and volcanic activity. We also think the way the liquid water actually exists on Europa is because it's so close to Jupiter that Jupiter tugs on the moon itself and actually changes how geology works on the planet as well. NASA has previously, Mark actually wanted to help me. I'm so proud. Oh, never mind. NASA actually previously had seen, it's okay, we're working with it, right guys? We're working with it. Thank you. Had previously seen plumes come out of Europa, which was an amazing thing. I can't stand there anymore. Which was a super interesting thing. So we're now gonna go to Europa and try to look for more of these plumes and better understand them. Okay, I'm on my last 2 slides. I'm honest. I feel like everybody wants to go out there and see the sky, and I'm the one holding you back. But this, again, blew my mind. You can see I'm really excited by science, but this kind of broke my brain as well. So similar to Mark, this is Mark. Similar to Europa, I'm sorry, Akanksha, I tried my best. I hope I don't disappoint everyone. Similar to Europa, there's a moon around the planet Saturn called Enceladus. Enceladus has a very, very similar structure like Europa. Oh, that's okay. So we also see plumes on Enceladus as well, which kind of shows that there might be liquid water underneath Enceladus. So here's the next generation mission by NASA. It's called EELS. It's called Extrabiology Extant Light Server. What you see over here is a prototype of it. I'm bringing down my voice because it's actually going to go up quite high. This thing is a robotic snake. What it's supposed to do is basically land on Enceladus, drill through the ice, and try to probe the water that's sitting kilometers underground. Okay, what I'm hoping for, the most comic thing that can happen is that there's a camera and it's continuously feeding back images to Earth, and it reaches the water and something just comes and takes it. That'd be pretty cool. I think it would make for a really good Netflix drama, if I'm right. All right, I'm towards the end of my talk. There's many more missions that are going on that are really bringing this particular field of astrobiology to life, to its maturity. And we're literally sitting on the cusp of finding some groundbreaking results. Here's what excites me about this. The first thing, nothing excites me. The first thing is, one more second. I think I'm getting faster at it, right? It breaks down, then I bring it back up. It's the technology. What happened? Oh, right. Hey, I just got that. It's the technology and techniques that are being used to actually understand these planets outside of our solar system. Making a robot to drill to kilometer thick ice on another planet. Perseverance had a helicopter on it. It's called Ingenuity. Flying a helicopter on using the atmosphere of Mars, that is very, very different. Understanding how light changes through the atmospheres of other planets. This is technology that may have direct implications to our day-to-day life. Astronomy has already proven that. Hubble, when it went up in 1994, had a problem. It was fixed by astronauts later, but that technology was later used to actually do laser eye surgery. This internet that we all enjoy, or not really, actually we do because you're listening to me through the internet, at least the people online, was developed at CERN. So these missions actually advance our day-to-day technologies and techniques. And I think that excites me really a lot. In fact, if I had $1 billion, that's what I would do, just buy new toys and play with them. But that's the second, and here's the second. A lot of the times, I'm an astrophysicist, right? I feel like that's been explained now. People ask me, why did you go and study astronomy? It has no practical output. Well, I just proved myself wrong in the previous slide. But here's something that I like to point out. It's the curiosity, I think, and that has a very, very profound output towards society. This is a graphic. It's not really very well shown over here by National Geography. And each circle that you see is an exploration mission around a body in our solar system. You can see we've been to the moon many, many times. We've been to Mars many, many times, and now we're going further and further away. Why are we doing that? We're doing that to understand our own place in this universe. Our own place in the universe. And I think that curiosity is something that keeps us away, that separates us from animals, and actually, on net, adds a positive to the society. I think that's something super exciting. I'm going to stop right there. I'm going to thank you all. Hold on. And I'm going to apologize for all of the technical difficulties, but I hope you enjoyed this journey instead of watching a Netflix drama. Thank you. The best thing is we don't need our slides. We can just have it. I have to stand here, sorry. This is much better, right?
First of all, thank you so much.
Thank you.
Fortunately, I want to do that. I want to ask you a question that is really well. Focus on sunlight stuff.
Right.
Well, again, I have to know the background. But when you're looking at red giant stuff,
right? Right. Yeah.
Are we looking at sunlight source because red giant is that the reason why we look for it?
Um,
hope that is not a-
no. I feel like for someone who says they don't have any knowledge, that's already a very profound question. So we look around red giant stars for one reason, and that I can very quickly think off the top of my head. Red giant stars are the future of what the sun will be like. The sun, of course, is evolving. It's continuously burning hydrogen into helium, and then neutrinos are coming. Wait, that's a completely separate talk. But that's how it's actually creating energy, right? But as it's actually processing through its energy, it's actually becoming a different and different star because it's using up the fuel. And at one point in time, it will become a red giant. So when we go and look at whether there could be planets around red giant stars, the best thing I can think of is to look at what the future of the sun will look like and what does that mean for the planets that that star actually hosts. Yeah.
And you said that they had found compounds in the atmosphere.
Yeah.
So I was curious what proved that it wasn't real and what was.
Well, no, so they did find phosphine. They definitely did find phosphine. Let's go back to Venus. So I think one of the key things over here is how much phosphine you find. So on Earth, phosphine is created in swamps. I stand close to the computer. And that's mainly it's the microbial life within swamps that creates that. But we also think through newer studies that are trying to understand astrobiology or life in extreme conditions on Earth itself, we think strong geological activities like volcanoes and things like that can also create phosphine. So the two things that changed in a follow-up study for phosphines on Venus was how much phosphine was found. So the amount that was found came down. And because now suddenly you don't have that much phosphine, it's very unlikely that there's organisms that are actually creating it. But secondly, because the amount came down, you could now also very easily say this was probably because of a volcano and not because of bacteria.
Thank you. You mentioned that Mars was inside our habitable zone, and you said there were conditions that Europa, so do you know if there are any missions to look into life?
Well, Percy is one of them. Percy is currently Perseverance. I love Percy, but sorry, Perseverance. That's what I call Percy. Perseverance is currently looking for signatures of life on Mars. Sherlock, the experiment that was there, it's the fancy word for it is basically a spectrograph. But what it's doing is picking up sand on Mars and basically trying to pass light through it and see, just like you see how we were doing that with atmospheres of planets, you can do that with actual solids as well. Just pass light through it and see light that comes out on the other end. Sherlock, the experiment on Perseverance, is looking for that to look for biological signatures. In 2021, when Percy landed on Mars, I was found to make a particular statement that if there was ever life on Mars, Percy is our last chance because of just the sheer technology that's on Percy. But now I don't believe that anymore because of how smart people are and how the new technologies that are coming out. So yeah, we're definitely very close to finding signatures. If there was life on Mars, we're not there yet. By the way, let me go back to the Venus question one more. I think we have time. It's okay. This thing, phosphines on Venus, that was quite interesting. It was later proven wrong, but it still actually ignited enough curiosity to go and study Venus again. So coming to us, hopefully, in about another 15 years, is another mission called Da Vinci. It's a mission funded by NASA and the European Space Agency, which is going to go study the clouds on Venus to better understand the clouds and whether if you could support life at different altitudes. Zoe.
When you were saying that we're looking for it, and all that we can really see is that the light dims as it passes. See if those planets are in the Goldilocks zone, because like It could just be like a really big one that's closer, or it could be a small one, like a big one that's here, a small one that's here, because it's just a shadow.
Right. So that's a very good question. Okay, it is very specific, but let me try and answer that. I think with this particular technique, you cannot tell how far away the planet is from the star, but we have studied enough planets around stars that we can make an educated guess of how far things should be based on the light that is absorbed by them. Most of the light that you see that is being absorbed by these planets is coming from planets that are gas, right? You do need gas, like in our atmosphere, to absorb that light. So when we do detect planets, most of these planets are what are called hot Jupiters. So they most likely don't have life. I think what I was trying to show with that is the idea that now we can do this 10 times further away, which is something super crazy. Now, actually, you know what? Because you've asked me this question, I'm going to show this. So JWST was able to actually see this particular planet. Yeah, perfect. Was able to see this planet and actually try and get the spectrum of that. You can see it's like just garbage, literally garbage. And we think this planet does not have an atmosphere. It's actually a rocky planet. And you can see the distance also goes down quite a bit. This is only 41 light years away. So this is still a very, very hard thing to do, but we're understanding these planets better and better. There was one back there, yeah. Yes, 100%. There's 120 billion galaxies. I don't have my calculator right now, but that's another like 1,000 billion type 3 civilizations that could be there. I think, so I moved away from other galaxies very, very quickly. And that's because no matter how much technologically developed we get, unless we are Matthew McConaughey traveling through a wormhole in Interstellar, we will never be able to reach more than 3 galaxies in the universe, okay? Space is really, really big. Traveling at the speed of light, which a certain Albert Einstein told me is not possible for us, is not possible for us, will take about 4 years for us to reach our nearest star. Oh, what's a pet peeve?
Like time travel slowly. When you can actually get to that star in a week.
Isn't that the twin paradox or something? Okay, anywho, a week. The Milky Way is roughly 110,000 light years. There we go. So yeah, it's very hard to travel through the Milky Way itself. So that's what makes it quite hard. Yeah. Oh, yeah, 100%. Why not? I don't see why not. They could have even visited us, but they could have visited us 2 million years ago or 3 million years ago or a billion years ago when the Earth was absolute hot mess, literally. And then said, oh, this is a useless planet, let's move on, kind of thing. That's actually one of the solutions to what is called the Fermi paradox, that the aliens actually came here, saw there was nothing and moved on. I'm happy, I think. But that's, I think, because of the fact that I've seen a lot of Netflix dramas. What's his name? Independence Day. Who's the star in Independence Day? Jeff Goldblum. Yeah. He didn't set a good example. Apparently, aliens are supposed to attack.
I think we have time for
Yeah. Yeah. How would, sorry, say that again.
How would one be able to tell, like, where the other one is?
Oh, that's a very good question. Most likely, it won't. I think if it's life as I defined within what is life, this is too many slides to go back on. One of the things was that one of the criteria for us as scientists to define life is stimuli, which means There we go. Which means that life will somehow develop techniques to figure out there's things around it. Think of a Venus flytrap. It's come up with sort of biological techniques to know that there is now a fly sitting on it, so it actually closes itself to start eating it, right? Do you have a sibling? Oh yeah? Okay. Every now and then when your sibling actually plays around with you and you get annoyed, that's a stimulus as well. I did that with my sister quite a bit. So yeah, so it's that's how, so depending on the organism itself and the surroundings, it will develop its own ways to figure out whether there's life around or not. You need that because you need to eat, right? Chickens are delicious, and we figured out we can eat them.
If you covered the sun with mirrors, would the earth not like start freezing?
No, we just use the energy, the cables that tied us to the earth, we use the energy from the cable to heat up the earth. Very simple solution. Come talk to me, I can develop a graph for you. Good.
Technically, the solution in my mind with absolutely no reason. You told that power to create a giant short circuit.
That's fair, that's fair.
Let's say thank you once again for a really great talk.